Hello, today we're going to be looking at lesson 5.4, which is our polygon mini lesson. So let's start by defining what a polygon actually is. This is important in understanding the remainder of the lesson. A polygon is a closed, plane figure formed by three or more segments. So a few key words there. Closed, meaning there's no openings or gaps. Plane, meaning two-dimensional. And then formed by three or more segments. That's obviously the case because in order for it to be a closed figure, you would need a third side to close it off. So 3 is the minimum. And a polygon, of course, is named for its number of sides. So I just took a small snippet of this diagram just to give you a feel for the way that our formula is derived that we'll be using throughout the lesson. So let's start with a triangle. And what I want you to see is that a triangle, of course, is made of three sides, and it contains just one triangle exactly. We know from our previous lesson that the sum of any triangle is 180 degrees. Next, if you look at a square, if you connect from vertex to vertex, is really two triangles, as you can see. And so the number of triangles contained in a square, or any quadrilateral for that matter, is 2. Now, because each of those two triangles contains 180 degrees total for its angle measures, that would mean that the sum of all of the triangles would be 360 degrees. And then if we take a look at a pentagon has 5 sides, and we can see here that if we start at one vertex and connect to all the others, we would have one triangle there, and then a third triangle here. So 1, 2, 3 triangles make up a pentagon, and the angle sum then would be 3 triangles, 3 times 180, which is 540 degrees. Now, the reason that this is all interesting and important is if you recognize any polygon, the number of triangles is always, because think about it, the number of triangles contained in the figure is always going to be 2 less than the number of sides. Because if we have a quadrilateral minus 2, there's 2 triangles. A triangle, 3 minus 2 is 1 triangle. A pentagon, 5 minus 2 is 3 triangles. And so that pattern allows us to determine the angle relationship or the angle sum of all angles in the figure. So this is known as the polygon angle sum theorem. And what it tells us is that the angle sum will be equal to n minus 2 times 180, where n is the number of sides. So basically, it's just saying that if you know the number of sides in a figure, you can subtract 2 to find the number of triangles. And then because that's the number of triangles contained in the figure, each one of those would have a sum of 180. So you just multiply by 180 to get your angle sum. Now, another important definition that we need to be aware of is a regular polygon, and all that means is that in a regular polygon, all sides and angles are equal. So we will certainly deal with many polygons that are not regular, but some of them will be. So let's practice using the angle sum theorem in example 1. So example 1 says, what is the sum of the angle measures for each of these polygons? So first it's going to be important that we identify what the figure is. So if we look at this first one, it has 1, 2, 3, 4, 5, 6, 7 sides. And so that makes this a heptagon, or septagon, depending on how you say it. So now if I want to use my formula, I know it's n minus 2 times 180. The parentheses are very important. You have to do the subtraction before the multiplication. And I would substitute in my number of sides. So I would have 7 minus 2, which is 5. And then 5 times 180, which is 900 degrees. So what that tells me is the sum of all of the angles in a heptagon is 900 degrees. I can do the same thing for my next figure over here, but first I need to figure out what it is. So when I count the sides, 1, 2, 3, 4, 5, 6, 7, 8 sides, that makes this an octagon. So when I use my formula, again, n minus 2 times 180, I would substitute in 8 for the number of sides. I would subtract to get 6. And then when I do 6 times 180, I will get my angle sum, which is 1,080 degrees. Okay, we'll take a look at example 2. Example 2 says find the individual angle measures in the regular polygon. So because we know in a regular polygon that these angles are all the same measure, we can actually call them all the same variable. So this would be x degrees, and so on for all 5 of those missing angles. Then I would want to find the sum. So for this 5-sided figure, it is a pentagon. I use my angle sum formula, and I do n minus 2 times 180. So I would take my parentheses around the n minus 2, just like we did in the last example, and I would substitute in 5 for the number of sides, and then I would have 3 times 180, which gives me 540 degrees. Now I can find the individual angle measures because I know that each of these x's have the same measure. And so that's because it's a regular. If we were not told this was a regular polygon, we would not be allowed to assume that, but we are in this case. So we have 5 x's. So if you think about it, the sum of all of those, x plus x plus x plus x plus x, is just 5x equal to the angle sum, will allow us to solve for what each of those x's are. So to solve this equation, we just simply divide by 5. And we get an answer of 108 degrees. So each angle of a regular pentagon measures 108 degrees. The next part of today's lesson is going to focus primarily on being able to classify and name polygons, but specifically quadrilaterals. So you'll notice in this table, we kind of have quadrilaterals are mostly classified based on their number of pairs of parallel sides. So we start with 3 just random quadrilaterals you'll see out here, and none of them have any parallel lines. So there are quadrilaterals that have no pairs of parallel lines. Some of them have names, like this one we call a kite, but others are just quadrilaterals. Then we have some quadrilaterals that have exactly 1 pair of parallel sides, and those are known as trapezoids. So you'll see over here, trapezoids have exactly 1 pair of parallel sides, and sometimes they have a vertical line or a right angle, sometimes they do not, so it just depends. There are different types of trapezoids, but the main thing you need to know is that they have exactly 1 pair of parallel sides. Then in this bigger oval, we have parallelograms. Now parallelograms have 2 pairs of parallel sides. So you have general parallelograms like these ones. They all look different, but the main thing we know is that they have 2 pairs of parallel sides that are across from one another. Within this family of parallelograms, however, we also have some special characteristics. So we have rectangles that are parallelograms that contain 4 right angles. So that means all of their angles are congruent. We also have rhombuses, which have 4 congruent sides. So they have 4 sides that are all equal in measure. And then we have an overlap. And the overlap exists whenever we have a parallelogram that has both the 4 congruent sides, like a rhombus, and the 4 right angles, like a rectangle. And that is known as a square. So a square is both a rectangle and a rhombus. Rectangles can be squares, rhombuses can be squares, but they are not always. Squares are always rectangles and rhombuses. Okay, next we'll practice classifying. So you want to take a look at the figure. Because it says give the name that applied to the figure, we want to probably start with the most broad name that we can think of. So when I look at this one, I know it's a polygon based on the definition we learned earlier because it is a closed plane figure comprised of two or more segments. So it is a polygon. Then I know polygons are classified by their number of sides. So when I see that this has 4 sides, I know I can identify it as a quadrilateral. I then know that quadrilaterals can be classified based on their number of pairs of parallel sides. I can see that this figure has 1 pair of parallel sides, which makes it a trapezoid. And once I identify a figure as a trapezoid, it cannot be any other figure, any other quadrilateral. So that is it. For the next one, I can pretty much start the same way. I see that it is definitely a polygon. It's a closed plane figure. Then, because that's classified by number of sides, I see this one also has 4 sides, so it is a quadrilateral. Now I know that quadrilaterals are classified based on their number of pairs of parallel sides. Well, I can see that this one has this set and this horizontal set, so it has 2 pairs of parallel sides, making it a parallelogram. And then I know parallelograms can sometimes be special, and this one happens to have 4 congruent sides, which I know from these single markings on the sides. So because it has 4 congruent sides, that makes it a rhombus. Now the only other thing that it could potentially be is a rectangle or a square. However, this could not be a rectangle or a square because it does not have right angles. So we would be done with those 4 names. Okay, the last problem we're going to look at, example 4, and this is a bit of a challenge. Notice we're looking this time for an interior angle measure. So we have this regular polygon. It is cut up into several pieces, and we have to figure out what the interior angle measures. So what we would first want to find is what is the type of figure. Now it says it's a hexagon, so that makes this somewhat easy for us. However, that's a typo. It is an octagon. Sorry about that. So this is an octagon because we can see that it has 8 sides. So then we're looking for the measure of angle x. So what we would want to do is find the angle sum of an octagon. And we can do that by just using our n minus 2 times 180 formula. So this would be 8 minus 2 times 180. And 6 times 180 will give us an angle sum of 1,080 degrees. Okay, now because this is a regular octagon, I can find each of these individual angles that make this up by writing an equation. 8, we'll call these all y. So 8y is equal to 1,080 degrees. Now I can divide by 8. And when I do that, I end up finding that each angle is 135 degrees. Now the reason this is important, if I know that this angle out here is 135 and this angle right here is 135, but I want to know angle x, what I want to take a look at is the fact that each of these individual angles must be half of 135, or together have a sum of 135. So either way, if you want to cut it in half and call it each individual one 67.5, you may. But that will allow us to solve for x. So now I could set up an equation because I know that this is an individual triangle formed and I'm looking for x. I could set up an equation of 67.5 plus 67.5 plus x equals 180. Combine these two, which I already know is 135. and then subtract 135 from both sides to find that x would be 45 degrees. So the interior angles of this figure we know measures 45 degrees.